So, hello everyone. My name is Diksha, and today we both are here to, present our work on the wind turbine fault detection system. So, as we all know, wind energy is one of the most promising renewable energy sources globally, but its, operational reliability is critical to meeting growing energy demands. So, through this project, we developed a system, to enhance turbine reliability by predicting potential faults before even they occur, ensuring a very steady supply of renewable energies while reducing maintenance cost and environmental impact. So, talking more about our project, let's start first with the problem statement. So, wind turbines, as a clean energy source, play a vital role in combating climate changes. So, however, their operational challenges, they often lead to unexpected failures. These failures can result in costly repairs, downtime, and disrupted energy supply. So basically, our approach was to address these issues by implementing predictive maintenance strategies, where predictive maintenance involves forecasting failures using data-driven methods, which enabling us to perform maintenance proactively rather than reactively. Next, let's talk about our data analysis approaches. So, for pre-processing the data, we used two major approaches. So, first one was variable analysis. So, in variable analysis, the key operational variables like wind speed, rotor temperature, and blade angles were identified as critical indicators. So, these variables directly influence, and they directly influence the mechanical and thermal stress experienced by the turbine components. The second approach we used was time series monitoring. So in time series monitoring, by analyzing how these variables change over time, we identified patterns and trends that might indicate early signs of failure. So, for instance, let's say a gradual increase in rotor temperature combined with abnormal blade angle could signal a potential mechanical issue. So, for a real time example, let's consider fluctuations in wind speed can lead to stress on the rotor, which might cause overheating over time. So, monitoring these variables in conjunction, with other, helps us to identify issues early. So, I'll show you the raw data we gathered. So this is the raw data that we gathered from the internet by doing all the pre-processing on this data. This was the clean data that we could acquire for our project. So here, data processing, as we all know, it is a very critical step in every machine learning project. So the raw data, which was this, that we collected from turbine, that it often contains noise values, missing values, and many outliers. So these issues can skew the result and reduce the model's accuracy. So to improve these, or to overcome these issues, we try imputing the missing values in this data set. We remove the extreme outliers using statistical thresholds like interquartile ranges. The next thing we did was standardizing variables to ensure consistent scaling across all the features. So doing all this, we were able to acquire this clean data, which had some newly added variables, which helped us get a better model accuracy. Next, talking about the data visualizations. So here you can see the first plot, which is cumulative power generation over time. So this graphic displays a consistent rise, as you can see, in power generation, which occasionally peaks or troughs, suggesting maintenance intervals or environmental indicators. Next up, we have uh, failure time categories by fault type. So, according to this stacked bar chart, we can see the fault type 2, which is the main cause of prolonged failures, highlighting regions that need urgent attention to increase turbine efficiency. So here we can see the third graph, which is a histogram. So this histogram with a normal, it is with a normal distribution centered at 0. The histogram and the density plot demonstrate that the majority of turbines maintain negligible temperature variations. However, the tails point to the impossible outliers, as you can see here. So yeah, so next up, talking about the methodologies, I would like my teammate to continue from here.
So, hello everyone, I'm Sharri Khatke. Now, let's discuss the methodologies which we have employed in this project. So, we have employed two methodologies. One is random forest classifier, and the another one is long short term memory. So, random forest classifiers were chosen mostly for their robustness and also in handling the imbalanced data, which is a common challenge which happens in fault detection system. So we specifically used balanced random forest classifiers and also easy ensembler classifier, which prioritized minority fault classes to ensure no issue is overlooked in the data. Now, in long short-term memory network, these are the types of recurrent neural networks which are designed for time series data. They excel at capturing temporal dependencies, which are very vital for monitoring the sequential patterns which happens in turbine turbine performance over the time. So together, these models offered complementary strength, with random forest providing high precision and also LSTM capturing nuanced temporal behaviors. So now, moving forward, we can see the results of the both the classifiers. So here it is a balanced random forest classifier. We can see the confusion matrix for it, and also we have achieved accuracy around 99%, which is a very good accuracy for this project. Now talking about the easy ensembler classifier, we also used this technique and achieved an accuracy of around 97%. Now, talking about the LSTM model, we can see the confusion matrix for this as well, and also we can see the plot which have loss over the epochs of like around 10 epochs, and also we have achieved an accuracy of around 98%. Now, talking about the results part, we highly encourage these techniques. So, talking about the random forest classifier, we have achieved 99% overall accuracy with exceptional fault classification performance across all the classes, including rare fault class like class 4. We handled the imbalanced data using the techniques like SMOT analysis, using the techniques like SMOT analysis to balance the data set and also to ensure the fairness across the classes. We also implemented some of the metrics such as precision, recall, and F1 score, and also confusion metrics to show the robustness against the real world classes. And talking about the LSTM model, we have achieved 98.1% of accuracy overall, which effectively identified sequential patterns throughout the data. Also, while LSTMs have excelled in with majority of the classes, but it also face challenges with minority classes, underscoring the importance of class imbalancing. Both methods demonstrated the good conversions during training, as evident in the previous graphs, as we have seen the loss over epochs graph. So this indicates that models were not overfitting and could generalize well to the new data. For we can I can give you one of the example related to this. Like for example, class 4 faults, which are the rarest but most critical, were accurately predicted in most of the cases, like in 97% of the cases, using the random forest classifier. Now, talking about the broader implications of this project, we can go beyond this. Like we can use predictive maintenance can be applied, such as some of the tech industries, such as manufacturing, to prevent the machineries which have to prevent the machinery breakdowns which happen in that industry. and in healthcare for early detection of equipment failures in the hospital. And also we can use this techniques in transportation to monitor the health of vehicles and to reduce accidents. So by leveraging these techniques, industries can achieve higher efficiency and reduce cost, and we can ensure the safety throughout the world. Our work underscores how data driven challenges is reshaping industries and driving us towards a more sustainable future. Now, finally, I can conclude this project by addressing some of the key challenges which we occurred in this project in wind turbine maintenance, and also demonstrated some of the power of machine learning in predicting the fault detection model. And we have also contributed to the broader goal of enhancing renewable energy reliability. Now, looking ahead, we can see the exciting possibilities such as integrating IoT sensors for real time fault monitoring and expanding these models to other critical systems. Now, thank you for your attention.
So thank you for listening to us, and any questions related to our project, you can reach out to us, and we shall be happy to, answer your questions. Thank you so much.